So in this next section, we're going to transfer to a branch of physics that deals with very different phenomena. We're going to talk about waves. So for starters, what is a wave? Well, it's a means of transferring energy from one point to another without transferring matter. So if you look at this wave in this image, you can see that the wave is traveling to the right. But this piece of material that's part of what makes up the wave isn't moving with it. So there's some work going on over here on the left-hand side of the image that's creating a disturbance, and then that disturbance is propagating to the right. But the material that makes up the wave doesn't move with it. So that's what we mean when we talk about the energy is transferring from one point to another. In this case, it's going from left to right. But the matter that makes up the wave doesn't travel with it as well. There are a series of ways that we can break up waves. And one way is to think about, well, what's the medium that they need to travel through? And so for electromagnetic waves, they do not need to travel through a material medium. They can, but they can also travel through a vacuum. And you know lots of types of electromagnetic waves, visible light being the one that you deal with most often. But radio waves, microwaves, infrared light, X-rays, gamma rays, all of these make up what are known as the electromagnetic spectrum. These are all electromagnetic waves. Mechanical waves, on the other hand, do need a medium. So there has to be some substrate of particles that the mechanical waves are going to use to propagate through space. Probably the most common example with mechanical waves are water waves. Sound is also a mechanical wave. The famous tagline from the movie Aliens, because in space no one can hear you scream. Well, that's because in space there's not enough particles out in space for the sound of your scream to propagate. Seismic waves within the crust of the earth, those are mechanical waves. Shock waves, waves on a string. So all of these are mechanical waves. There has to be a medium that they're traveling through. If we want to talk about a mechanical wave is a disturbance that travels through a medium and transports energy from one location to another without transporting matter. So again, we're still building on that basic definition. We're just adding in a little bit more detail here that in talking about a mechanical wave, our disturbance needs a medium to propagate through. If that disturbance is a single event, like what's pictured here, we have a wave pulse. And so you might watch this pulse, again, travel to the right. If the disturbance comes from an oscillating source, then you get a continuous wave. And so here, as your source keeps vibrating up and down, you end up with a continuous wave that travels off to the right. Well, once we've got mechanical waves, we can break those up into various types based on the direction of the disturbance relative to the direction of travel. So in this case, you'll notice that for both of these waves, they're traveling to the right. But this first one is known as a transverse wave because as the wave travels to the right, the particles move up and down. So this is what that initial image was showing, was a particle bouncing up and down while the wave moved from left to right. That's a transverse wave. In our heads, when we picture a wave, a transverse wave is almost always what that image is. A longitudinal wave, again, this longitudinal wave is still traveling to the right. It's just that now the disturbance is parallel to the direction of the wave propagation. So your particles are bouncing back and forth along the direction of the wave. So if the wave's traveling to the right, your particles are bouncing back and forth to the right. So with our transverse waves, again, this is the picture that most of us have when we think of a wave, something that looks like this, right? And there's some points within this curve that we should label. So for starters, we can talk about the crest. These are the peaks of the wave. The troughs are the low point of the wave. We can also talk about a couple of distances. An amplitude is the distance from the center line of the wave to either the peak or the trough. So I can measure the amplitude from the center line going up or from the center line going down. In either way, I should get that same distance. I can also measure the wavelength. And so the wavelength just tells you how far do you have to travel before your wave starts to repeat itself. So again, part of what's going on is we have a very repetitive pattern here. How far do you have to go before that pattern starts to repeat? So to measure that, you can go from peak to peak. That's one way to measure the wavelength. You can go from trough to trough. Again, that'll measure the wavelength. You can also go from center line through the center line again and come back so that you've gone through a full wave. So if you start at the center line, the one thing is it's not just the next time you get to the center line like it is at either the peaks or the troughs. It's the next time you get to the center line going in the same direction. And so that's true for any point that isn't a maximum on this curve. So these are transverse waves. Longitudinal waves, again, what's happening is your stuff is bouncing back and forth horizontally as the wave travels horizontally. And so instead of setting up peaks and troughs, what you set up are known as compressions, where your stuff is smushed together, and rarefactions, where things have spread out. So if I were to take a spring, and instead of swinging up and down with the spring, if I were to grab some of it, pull it back towards myself along the spring, and then let it go, what you would see is you would see the coils of the spring basically scrunch up and spread out as that wave pattern moved back and forth along your spring. That's what this image is showing. And so your compressions, you can think of them as like peaks. Your rarefactions, those are like the troughs. And so again, your wavelength, well, go from center of your compression to center of your compression. That's one way to measure the wavelength. Go from center of the rarefaction to center of the rarefaction. That's another way to measure the wavelength. So we still have that same distance. You could, of course, also measure an amplitude, but that amplitude is now along the spring rather than across the spring.